Okay, so in this video, we want to consider the concept of linear independence, and you may wonder, well, how does this relate to our discussion in the previous video? Well, if you remember what we did with linear combinations, the idea was to take an object that contains an infinite number of points, such as a line or a plane, and to reduce those objects to a very small number of vectors. So any line in the three-dimensional space can be boiled down to a single vector, and any plane can be boiled down to two vectors. Now, what we want is, given, and we'll see more examples as we move on, we'll have these spaces that contain an infinite number of elements, and we'll try and boil them down, reduce them to a small number of vectors. And we won't just be happy with a small number of vectors, we will want the smallest number of vectors possible. So think of it this way. If I give you, say, a line in R3, well, one vector is enough to generate the entire line, right? If you take all possible multiples of one non-zero vector, you trace a line in R3. So you wouldn't want to boil down a line to two vectors if one vector is sufficient. In the same way, you would not want to boil down a plane to three vectors or more if only two vectors are sufficient. So the idea is, how do we take an object that consists of an infinite number of points or elements, and how do we reduce it, boil it down to not just a small number of vectors, but the smallest number of vectors possible? And this is what linear independence will give us. So let's define linear independence and see how it relates to our goal of reducing these infinite objects to the smallest number of vectors possible. So suppose you have m vectors, v1, v2 through vm, in Rn, sorry. So let these m vectors be vectors in Rn, therefore vectors with n components, and we have m of them. We say that, this is our definition, the vectors v1 through vm are linearly independent if the equation and here's the equation. We are going to ask, how can we obtain the zero vector with a linear combination of these m vectors? So if the equation c1 times v1, so some multiple of v1, c1 is a real number, plus some multiple of v2, up to some multiple of vm, being equal to the zero vector. So this is our equation, expressing the zero vector as a linear combination of these m vectors. So here the vectors are fixed, and we're trying to solve for the coefficients. How many solutions are there to this linear combination being equal to the zero vector? So we say that the vectors are linearly independent if the equation has only the trivial solution. Well, what is the trivial solution? So we're saying that this equation, the vectors will be linearly independent if this equation has a unique solution, has only the trivial solution. Thus, what is the trivial solution? Every coefficient must be equal to 0. So that's c1 equals c2 equals up to cm equals 0. If this is the only solution, or if you prefer, the unique So think of it. Given any vectors v1 through vm, obviously, if you choose c1 to be 0, c2 to be 0 up to cm, well, 0 times any vector is going to be the zero vector. So clearly, if you set all the coefficients, C1 through Cm, to be equal to 0, clearly this linear combination is the 0 vector. And the vectors are linearly independent if this is the only solution. Now, if we have a non-trivial solution, we say the vectors are linearly dependent. So if there is a non-trivial solution to this equation, so let's call this star. So if star has a non-trivial solution, we say that the vectors are linearly dependent. Oops. And think of it. What is a non-trivial solution? Well, the trivial solution means every coefficient has to be 0 to solve this equation. Non-trivial means that at least one of the coefficients must be non-zero. And that is a non-trivial solution. Okay, so this is our definition. Given m vectors, consider a linear combination of these m vectors giving the 0 vector. If the only way to obtain the 0 vector with a linear combination of these m vectors is with letting every coefficient being equal to 0, the vectors are said to be linearly independent. If there is at least one solution where one of the coefficients is non-zero, you have a non-trivial solution, and the vectors are said to be linearly dependent. Now the question is, how would you, given explicit vectors in Rn, how would you verify whether or not the vectors are linearly independent or dependent? Well, let's just rewrite this linear combination, right? We know that we can always rewrite a linear combination being equal to a vector in an augmented matrix form. So if you write C1v1 plus C2v2 up to Cmvm being the 0 vector, you're asking, can we express the 0 vector as a linear combination of these m vectors? And we know this is equivalent to solving the linear system, right? Because we are given the vectors v1 through vm as fixed vectors. The variables are the m coefficients. And we know that solving this linear combination is equivalent to solving the linear system whose variables, well, again, we're trying to solve for the coefficients. So the coefficients are the variables. The constant terms, well, are given by the 0 vector, so all of these are zeros. So we have a homogeneous linear system. And the multiples, the constants for C1 are the entries of V1. So V1 is the first column of our matrix of coefficients. Then it's V2, second column, up to Vm, giving us the mth column of our matrix. We can call this matrix, say, A. And that's it. So whenever you're given vectors in Rn, and you're asked, are they linearly independent or dependent, go back to the definition, trying to express the 0 vector as a linear combination of these m vectors. And of course, this equation is equivalent to solving the linear system, where the variables are the coefficients, and the vectors v1 through vm form the columns of your matrix, and the constant terms are all 0. And now imagine reducing the matrix and solving the system, right? If there is only the trivial solution, therefore C1 equals C2 equals up to Cm equals 0, that means a unique solution. Therefore, every variable must be a leading variable. Therefore, when you reduce the matrix, every column will have to contain a leading 1, right? The only way to have a unique solution is if each variable is leading. So if you row reduce this matrix and every column has a leading 1, then every variable is leading. Therefore, you have a unique solution being the trivial solution. Therefore, you have linear independence. On the other hand, if you reduce the matrix and at the end, one variable does not have a leading 1, it will be a free variable. And because the system is homogeneous and we always have at least a trivial solution, you'll have a free variable, therefore an infinite number of solutions, therefore you will have linear dependence. And that's it. This is how you check whether or not vectors are linearly dependent or independent. Now it's worth making a few observations, at least 2 simple observations, and then we'll go back to the term independent and dependent, and why are we using these 2 adjectives. Let's look at just 2 simple facts. Because sometimes, if you're given vectors, and the question is, are they linearly independent or dependent, we know that we can always fall back on going through the definition, rewriting the equation as a linear system, solve the system. If every variable is leading, you have a unique solution being the trivial solution, therefore independence. If one variable is free, therefore missing a leading 1, you have an infinite number of solutions, therefore linear dependence. But the question is, do we always have to row reduce, or are there sometimes shortcuts? And the answer is yes. There are 2 special cases when there's no need to row reduce the matrix, and we can claim right away that we have linear dependence. So fact number 1, or fact A, if one of the vectors is the 0 vector, the vectors are linearly dependent. So if 1 of v1, v2 through vm is the 0 vector, then the vectors are automatically linearly dependent. Why is this obvious? Well, let's look at this in 2 different ways. We're saying we have m vectors, and we're saying if one of these vectors is the 0 vector, then the vectors are automatically linearly dependent. Let's go back to the definition. Imagine that if, say, v1 is the 0 vector, well, set c2 up to cm to be all zeros, so this goes away. Then you're left with a multiple of the 0 vector being the 0 vector. So c1 could be 1, because 1 times the 0 vector is the 0 vector. c1 could be 5. 5 times the 0 vector is the 0 vector. And you see that you have an infinite number of solutions. Therefore, linear dependence. Or look at the linear system. If one of the vectors is 0, say again vector v1, no matter which operations you use to row reduce the system, this will always remain a column of zeros. So you'll never have a leading 1, so guaranteed c1 will be a free variable. Therefore, you'll have an infinite number of solutions, therefore linear dependence again. So if you ever have a set of vectors, and one of them is the 0 vector, don't do anything, automatically they are linearly dependent. Another shortcut, and that is, if, let's recall that we have taken m vectors in Rn. So we consider m vectors, v1 through vm in Rn, and let's assume that we have more vectors than n. So nm is strictly bigger than n. So these are our 2 assumptions. We have m vectors in Rn, and we have more vectors than n. Then, the conclusion is the same as part A. The vectors are automatically linearly dependent. So if you ever have a set of vectors in Rn, and you have more vectors than n, there is no need to solve the linear system. Automatically, the vectors are linearly dependent, and that's it. Now think of why this is true. As always, go back to the definition, the equation being a linear combination of the m vectors giving the zero vector. Look at the linear system, and now think of it. If the vectors are in Rn, that means that the length of the vectors is n. There are n entries. But when you row reduce a linear system, we know that a single row can contain at most one leading one. Sorry. So if the vectors are in Rn, this matrix consists of n rows. Therefore, we have at most, in the best case, n leading ones. But we have m variables. So if we have more variables, then we can have leading ones. Not all variables can be leading variables. At least one variable will be a free variable. Therefore, the system has an infinite number of solutions. Therefore, the vectors are linearly dependent. And that's it. So always remember these two shortcuts. If you're checking for linear dependence or independence, if you have the zero vector, dependence. If you have more vectors than components of your vectors, therefore n, also automatically the vectors are linearly dependent. If that's not the case, either A or B, then you have no choice. You have to row reduce, and then it's a case by case. Let's look at one result as to why we're saying that the vectors, why are we using the adjective independent and dependent? And it will be clear from our next result. And this is a theorem, which again will make it clear why we are using the term independent and dependent. So the vectors again, let's assume we have m vectors in Rn. These m vectors are linearly dependent. If and only if, so now we are giving an equivalent statement. The vectors are linearly dependent if and only if, and this will be a more intuitive notion, if and only if one of them is a linear combination of the others. So at least one and then the word dependent makes perfect sense. Because if one vector, at least one, is a combination of the others, then you can build that vector from the other vectors. So of course that vector depends on the other vectors. And this is a perfect equivalence. Therefore, the two statements may look like we're saying something different, but they're either both true or both false. So let's prove this, and the proof is very easy. What's important in this result is to remember the actual statement. Vectors are dependent if and only if at least one is expressible as a linear combination of the others. So at least one of these vectors will depend on the others. As always, when we have a proof of equivalence, we have to prove the two directions. Let's start with proving this direction. So we'll prove that if at least one vector is a linear combination of the others, we will have linear dependence. So this is our assumption. Now, which vector is a combination of the others? Is it v1 that is a combination of the others, or is it v2? Well, it doesn't really matter. Whichever one it is, you can always relabel the vectors, So we can assume that v1 is a combination of the other vectors. So suppose that v1 is a linear combination of the other m minus 1 vectors. So say v1 is equal to some multiple of v2 plus some multiple of v3 up to some multiple of vm. And from this equality, v1 being a linear combination of the other vectors, we want to prove that we have linear dependence. Well, again, this is considering a linear combination of these m vectors giving the 0 vector. Well, all we have to do is send v1 on this side, and we'll get the 0 vector equals negative v1 plus these vectors. So negative v1 plus a2 v2 plus a3 v3 up to am vm is therefore the 0 vector. But look at what we have here. We have a linear combination of the vectors v1, v2, v3 up to vm giving the 0 vector, and this is a non-trivial solution. Right? We don't know what a2 is, what a3 is up to am. These could all be 0 for all we know. But look at the coefficient of v1. Call this c1, which is negative 1, which is not equal to 0. So you see that we have a non-trivial solution to the linear combination of our m vectors giving the 0 vector. Therefore, by definition, the vectors are linearly dependent. And this proves the one direction. If one of the vectors is a linear combination of the others, automatically we have a non-trivial linear combination of the m vectors giving the 0 vector, and therefore the vectors by definition are linearly dependent. Let us prove now the opposite direction, that if the vectors are linearly dependent, at least one vector will be a combination of the others, and that is the other direction. So the assumption is that the vectors v1 through vm are linearly dependent. Well, by definition, this means that the linear combination of these vectors giving the 0 vector has a non-trivial solution. So this is our only assumption. So the equation c1 v1 plus c2 v2 up to cm vm being equal to the 0 vector has a non-trivial solution. Well, what is a non-trivial solution? Again, the trivial solution means every coefficient must be equal to 0. Non-trivial is the opposite of that. Well, the opposite of every coefficient being equal to 0 is at least one coefficient is non-zero. So the fact that this equation has a non-trivial solution implies that at least one ci is not 0 for some I. Maybe it's c1 that's not 0, maybe it's c2, or maybe it's cm, we don't know, but at least one of them will be non-zero. So for some choice of I between 1 and m. So now the only question is, well, which one is it? Is it c1 that's not 0? Or is it c2 or c3 up to cm? And if you think of it, it doesn't matter. Whichever one it is, suppose it was c3. Well, move c3v3 instead of c1v1 and send c1v1 to c3v3. And so you can assume that c1 is the coefficient that's not 0. Because whichever coefficient is not 0, move it as the first coefficient, and therefore c1 will be non-zero. So we can assume that C1 is the one coefficient that's not 0. There may be others, but we only need one. Now think of it, what is our desired conclusion? We want to conclude from this that at least one vector is a linear combination of the others. Well, if C1 is not 0, we can isolate C1v1. So, subtract everything here and send it on the other side, and you will get that C1v1 is equal to negative C2 times V2, negative up to negative Cm times Vm. And because C1 is not 0, we can divide or multiply across by 1 over C1, and you will get that V1 is equal to negative C2 over C1 times V2, negative dot 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 up to negative Cm over C1 times Vm. And look at what we have here. Because the vectors were linearly dependent, we had a non-trivial solution. Therefore, at least one of the coefficients was not 0. We said assume that it's C1 that's not 0. And we were able to solve for V1 as some real multiple of V2 minus some real multiple of V3 up to some real multiple of Vm. Therefore, V1 is a linear combination of V2, V3 up to Vm, and this proves our conclusion. V1 is a linear combination of the other vectors. This concludes the proof of equivalency. So two vectors can only be, not two vectors, but a set of vectors can only be linearly dependent if at least one is a linear combination of the others. So if at least one vector can be built from the other vectors, therefore one vector depends on the other vectors. And one last little remark. Which is simple but also useful. What if we looked at this result and assumed that we only had two vectors v1 and v2? Therefore, the two vectors would be linearly dependent if and only if at least one is a combination of the others, but therefore that would be at least one vector is a combination of the other. There's only one other vector. So two vectors are dependent if and only if one is a multiple of the other, therefore if they are parallel. This is a small remark, but a useful remark nonetheless. So two vectors, let's say v1 and v2, are linearly dependent if and only if, and we'll state this in two ways. We know from the previous more general statement that vectors are linearly independent if one is a combination of the others, but again there is only one other. So if and only if v1, because if one vector is a multiple of the other, they are parallel. So if and only if vectors v1 and v2 are parallel, or if you prefer, v1 is some multiple of v2. So whenever you have two vectors and you're asking are they dependent or independent, very easy. Ask yourself, is one vector a multiple of the other? If the answer is yes, they are linearly dependent. If the answer is no, they are linearly independent. And as we'll go through more and more examples, we'll see that whenever you have an infinite object and you reduce it to a finite set of vectors, if those vectors are linearly independent, you have reduced the infinite object to the smallest number of possible vectors. And that's why linear independence is such an important concept.